chapter 22 or 23. This is going to be part 3. Okay, we were alkylating amines and we saw the cyanide group being reduced. We saw the azide group being reduced. We saw the nitro group on the benzene be reduced. And finally, in the previous part, part 2, we saw the Gabriel synthesis. All of those were to make primary amines. So how do you make a secondary or maybe a tertiary amine? This is a very good way of making, well, this one actually allows you to make primary, secondary, or tertiary amines, and it's called the reductive amination. And it's using an old reaction we saw in the ketone and aldehyde chapter, because if you have a carbonyl of a ketone or an aldehyde, and you have a nitrogen, we are going to do a condensation reaction. And this nitrogen has 2 hydrogens, so I'm going to eliminate water. And I'm going to attach the nitrogen where the oxygen was. So this is what we call an imine. This one is with ammonia, so I have an NH at the top. This is methylamine, so I take the 2 hydrogens off to make water. And we are going to put the nitrogen with the methyl where the oxygen used to be. So this is another imine right here. So both reactions gave me imines because I had 2, and in this case 3 hydrogens attached to it. So it's straightforward, the elimination of water. Alright, so I need to get rid of the double bond, and there's 2 possible ways, 2 effective ways of getting rid of the double bond. The first one is just a hydrogenation reaction. So we're going to hydrogenate using nickel in here, and the pressure that we're going to use is 90 atmospheres of hydrogen right here. Now notice that this is an equilibrium reaction, so at any given point I have aldehyde and I have the imine in here. So this is more selective towards the carbon-nitrogen double bond. I have to take into account that I do not want to reduce the aldehyde. I want as much amine as I can get as product. So this is a primary amine, this is benzylamine. Another reagent that we can use is sodium cyanoborohydride, NaBH3, and a cyanide. It's the cousin of sodium borohydride, but one of the hydrides have been replaced for a cyanide. And basically the cyanide is going to render the hydride less reactive, because the cyanide is going to be slightly electron withdrawing, so the hydrides are going to be less basic. Now this reaction is best done at a pH of between 2 and 5. Well, no, between 2 and 3. But the sodium cyanoborohydride, again, it takes care of this equilibrium right here because it prefers the carbon-nitrogen double bond. So it will not touch your cyclohexanone. It will reduce the imine. So in this particular case, I get a secondary amine out of that reduction, out of the reaction. If you wanted to react with a secondary amine right here, you would get the N-amine, and the N-amine is a carbon-carbon double bond with, so hydrogen and palladium will get rid of it. But the reductive amination allows you to make primary, secondary, and tertiary amines. This is an amide. It's a primary amide. Notice my nitrogen has 2 hydrogens and only 1 carbon attached to it. And we're going to do the Hofmann rearrangement. Notice that the Hofmann rearrangement, it starts with an amide, so I'm not putting the nitrogen on a carbon. I'm not attaching it. But I need a basic solution of bromine. That means I need bromine and base. And what's going to happen is that what you and I usually call the alpha carbon of the amide, it's going to end up attached to the nitrogen. So we are going to lose CO2 in this reaction. So here's your alpha carbon. We're going to eliminate the carbonyl as CO2. And now you have your cyclopentanamine. Let's do a little problem right here. This one has two amides. Again, the requirement for the Hofmann rearrangement is that the amide is primary, so I have to have two hydrogens attached to it because we're also we're eliminating water in the process. I like to mark my alpha carbons, that way I don't get lost in what we're doing, because what we're doing is that we're going to attach the nitrogen to the alpha carbon and we're going to lose CO2. Now you need an excess of the basic bromine. And you do the reaction. It's a Hofmann rearrangement. Now Hofmann was, or it still is, at least his name is very widely known, he's long dead, but he used to actually do a lot of reactions with amines, so he has a second reaction with his last name on it. Again, this one is a rearrangement, the one that we lose CO2 and we start with an amide. The second Hofmann reaction is a Hofmann elimination reaction, and this one takes a little longer. The mechanism is longer, so I'm going to go step by step. This is a primary amine. It doesn't need to be a primary amine to begin with, but here's what we're going to do. We're going to the first step of the elimination is that we're going to put as many methyls as we can on this nitrogen. It's called the exhaustive methylation reaction. And you just use a large excess of methyl iodide and a little bit of well, you need a base, so if you have the bicarbonate or the carbonate, that's perfectly fine. So what we're going to do, we're going to replace the hydrogens on the nitrogens for methyls, and we're going to add one more methyl. So I have two, so I replace two hydrogens for two methyls, and we add one more, so I end up with three. The nitrogen is now an ammonium salt. It's positive, so it has a counter ion. And I need to point out the counter ion because we're going to change that counter ion. So we're going to use silver oxide and water. This is what they call wet silver. And when you actually just mix silver oxide with water, you make a little bit of hydroxide, not sodium hydroxide, of the hydroxide ion. I'm not changing anything. I need to write the hydroxide because the hydroxide, it's going to be the base that we're going to use to make a double bond. Alright, so the wet silver that I have right here only exchanges the iodine, the counter ion for the hydroxide counter ion. And now we're going to do the reaction. So what we're going to do is an E2 elimination. You're good at that. This is the alpha carbon, this is the beta carbon. I'm going to extend one of the hydrogens on the beta carbon. So this one's going to be 1. And I put up the other one. Because the elimination, it's going to be promoted with heat. So I'm going to start heating this, and the hydroxide is going to be the base that's going to go to the beta carbon. It's going to form a double bond between the beta and the alpha carbons, and that's going to kick out my leaving group, the trimethylamine leaving group. The nitrogen is positive, so it makes for an excellent leaving group. So what I am left with, I'm going to make an alkene, and I'm going to have a double bond right here. So I have a CH double bond CH2. The hydroxide picked up a proton, so I have water as a byproduct. And my leaving group is triethylamine, so it's also going to be in solution. But this is a product that we're going after. So we're going to make an alkene out of this. And I need 3 steps. Step 1, exhausted methylation. Step 2, wet silver. And step 3, heating. The heating is what's going to promote the elimination. If you don't heat it up, you're not going anywhere with the Hoffman elimination. All right, now Hoffman noticed something very particular about the double bond that he was making, and is that every time you do the Hoffman elimination, the major product is going to be the less substituted double bond. So this opposes what we learned the first semester and what we call the side-Ceph product. So side-Ceph is the most substituted double bond as the major product. The Hoffman rule is the less substituted double bond as the major product of the reaction. So let's do a problem that actually makes 2 different double bonds. All right, look at this amine right here. The nitrogen has already been methylated. So I have 3 methyls and I have a big group right here. The 3 methyls, those are going to be staying with the nitrogen. So what I'm going to do is that I'm going to mark the alpha carbon, and in this particular amine I have 2 betas. I know that the double bond is going to be between the alpha and the beta, and if I have 2 betas, I have 2 possible double bonds. I have already apparently reacted with wet silver because I have the hydroxide counterion, which we're going to use as a base. And all I have to do is make the double bond because I'm already heating this up. That's all that I need to do, heat it up. All right, so I'm going to make my 2 possible double bonds. So maybe it's between this carbon, the beta and the alpha right here. Or maybe it's in between. Now we have to determine which of these 2 double bonds is the less substituted double bond. This double bond right here has 2 methyls attached to the double bonded carbons. So it's a di-substituted double bond. There's my double bond right here. I have an ethyl attached to my double bonded carbon. So this is a mono substituted double bond. The less substituted double bond is going to be the major product of the reaction. So this is the Hoffman elimination, and remember that in the Hoffman elimination, the less substituted double bond is going to be the major product of your reaction. Are we good? All right, let's do one more.